Hello? Yeah? I think we're ready, right? So, hello everyone. Thank you for coming today. Well, it's a beautiful Saturday and you have other options. You also had your bed. And somehow we all decided that being here talking about Git would be better than that. So, I guess we either love Git or we are in a desperate situation. But I know we all love Git, right? So I hope I don't disappoint you too much with this talk. My name is Manu Magalhães, and you know, I quite like information. It's such a powerful thing, isn't it? And somehow I've always been working around information in different ways over time. I started as a journalist, and then it morphed into translation, and in its present form, I work protecting information from source to screen to sky. So my goal today is to help us use Git as a tool rather than as a set of magic spells. We'll be looking at Git nuts and bolts to master it from the inside. And just let me put it out there, I am no expert, okay? I'm just someone who got fed up with not knowing what the heck is going on, and I came back to report. So thank you. So I'll share here today what broke the spell of Git for me, and I hope that this will help you too. So just let me stress this, there is no magic at all. So it wouldn't be surprising if our Git mental model were a bit like this image there, you know, Git as a collection of confusing, dangerous barbed wires, and you know, each spike is a commit, each wire is a branch, and they get entangled by default. And they work, but unless we want to bleed to death, it's better not to mess too much with it, right? And well, it could be understandable if we have some kind of mental model like this, because most often than not, when we learn Git, we are just told, you know, Git has something to do with version control, and there are commits and branches, but don't worry, just use this set of commands and you will be all right. Okay, does it ring a bell with anyone? Well, so today I would like to propose a different mental model that is a bit more accurate and a lot more friendly. So in 2011, the British documentary Wasteland was shortlisted for the Oscars. It showed how the Brazilian artist Vic Muniz created a network collection called Pictures of Garbage. Vic Muniz worked in collaboration with garbage pickers in Rio in what was the largest dump in the world by the time. And, well, he gave them the profits, well done. And he created images on a massive scale and used it to discarded objects like tires, wires, toilet covers, and so on to compose the image. And the final product was a series of photos taken from above, showing the whole picture. And you can see there the shed where the work was carried out, and there one of the final pieces. And well, this is pretty much how Git works. And this is the mental model that worked for me. And please don't get me wrong, I'm not implying that your code is rubbish. No, I'm just saying that like the garbage pickers, we are constantly adding, removing, replacing objects, and together they create this big picture that is then photographed as a final masterpiece. And that's Git's secret. Git is a series of snapshots that shows how each object looks like at a certain point in time. And I'll say that again because that's the really core of Git. It's a series of snapshots that show what each object looks like at a certain point in time, just like pictures of garbage. And this is really what sets Git apart from other version control systems. And this mental model is also helpful because it corrects a misconception that Git is a version control system that keeps track of your files, like some sort of backup, or that Git only tracks changes to the files. So to make this clear, Git does not track your files at all. Git tracks content. Content is the soul of Git. So if you doubt it, let's check the man page. It says there, Git, the stupid content tracker. They are the ones saying that, not me. And this means that the building blocks of Git are not your files or your folder structures or diffs, but your actual content. And there's something that I need to show you first before we dig deeper into Git. You see that? Is that better than magic? I don't think so. But that's just my name, Manu. But it has been hashed. So a hash is what happens when you pass some data through a formula. Hashes are generally a string of characters, and no matter how big or small the original data is, hashes that use the same formula will always have the same size. So if I hadn't told you that this is my name, you would probably never guess, because it's virtually impossible to determine what was the input based on the value of the hash alone. And here's a quick example. You can see the word fox in the top. It's only 3 characters, and when we pass through the hash function, it creates an output of 40 characters. And the same happens to the sentence below it, which has way more characters. And the output is still 40 characters, just letters and numbers. And another thing is that no matter if you do like just a tiny bit of a change, like in the last sentence, we removed one of the letters. No, we changed. But you see the output is completely different. So really there is no way for you to crack it. Microsoft took I don't know how many years to crack a SHA-1 that is one of the ways you can hash stuff. So a regular person will really never get this. But why are we even bothering about hashes? That's because hashes are, Git owes its life to hashes. Although they are mainly used in security context, for Git, hashing is a way to identify files and objects and ensure that they are, they have integrity. And you will see that. We will give you some demonstration. But by now, let's explore the anatomy of a Git repo, because I think that's the best way for us to understand the inner works of Git. So this is a screenshot, and I would like you to think through for a moment where my repo is in this screenshot. Would my repo be these 3 files, like Mama Stop Wannabe? No, those are just, files with content inside. Would it be the red Spice Girls over there? No, that is my branch. Oh, Manu, don't be silly. Everybody knows that, your repo is my lyrics, right? No? Sorry, this was a gotcha. My repo cannot be seen there because by default, Git repos are hidden. So let's take a look at what a repo really looks like by creating one. So this is an empty directory called countries, and I'll run git init on it. And if we list the hidden contents of the directory, we will find our repo. So you see there, .git, that is my real repo. And remember, this is a brand new repo, we just created it. Do you expect it to be empty or have something inside? And if there is something inside, what kind of things would it be? Okay, let's explore it. So let's just clear the screen and let's run the ls and who. I don't know if this is the first time you see a Git repo from the inside, but in my first time I was really surprised to see all these things, and even more surprised that I didn't recognize any of those names. It didn't ring a bell at all. So we can see there that we have 3 files and 4 folders. So the files are the 3 top ones in white, head config description, Head is a bit too important for us to address right now. We'll leave it for later. Description is not important at all because it's just something that is used by some obscure web interface that Git has, and I don't know anyone who uses it, so we don't need to look at that. So the file config, that is an interesting one. This file config has configuration options that are specific to your project. So for example, I'm doing this demo, but I want to keep my username in Git private and my email private. So I can run commands that will change my name and my email, and this information will be kept in this file config. So let's see how it works. Okay, let's clear a bit this and run git config user.name and then create some name like Shuri. And do the same for an email. Let's create a fictional email for a fictional character. So Shuri is an Avenger. And yeah, then we have it. And now if we cut the config file, you see in the bottom that, now my name is Shuri and my email is shuri@avengers.wk. So for the duration of this project, I am a princess of Wakanda. Thank you very much. And now let's look at the folders. We've seen all the Git files. And now let's see the folders. Let's bring it back. And we have hooks, info, objects, and refs. Right, so the hooks folder is for hook scripts, which we're not going to explore today. But I think it's worth mentioning because there's a very interesting use case for hooks, and I think everyone should take a look at it. It's a case for pre-commits. When you use hooks, you can tell Git what to do before a certain action, for example. So with a pre-commit hook, you can prevent people from committing secrets to the code. So that's a way to keep your Git history clean from secrets. So yeah, I really recommend you exploring that. Then we have the info folder. The info folder contains a file that is called exclude. And this file works similarly to a git ignore, but it's mainly for things that you want to ignore for yourself. You don't want to impose this ignore on other people. So it's really for private and for this project. So if there is anything, your colleagues like to add some stuff and you don't want to see them, you can use exclude. And then we have the tastiest folder of all, which is objects. And please, this is the folder that you don't want to delete whatever happens, ever, because this is where all your files will live. Your content will be all there in objects. And this project is brand new and empty. And again, I ask you, do you expect anything to be inside objects? At this point, everybody's second-guessing themselves, right? So let's see if there is anything there. We can use this search for regular files inside the git./objects folder, and we will try to find type files. And ta-da, it's empty. So let's create a file called chili, for example, and try again. Oh, it's empty. Why? Well, let's see if Git status can help us in this case. You see chili is red and it says untracked files. That's because Git only starts to pay attention to your files once you add them, and you need to do git add to that. And if we run again, you see this very long line of letters and numbers. Does it ring a bell with hashes? There is a slash there, but that's just because Git takes the first two words of the hash to create a directory, and it's just really to make the search for hashes quicker. But yeah, there you have it, your very first Git object. And let's go ahead now and commit this file and check if anything changes in our object folder. So commit, just like a regular message, add chili. And okay, now we will see if, oh, we tripled. But why? We just committed. What are all these extra files that appeared on the folder? Well, helpfully, Git has a special command to help us identify what type of object these hashes represent. So this -t is just to give us the object type. And we see there that we have a blob. We also have a tree. And, sorry, I'm slow at typing. I have a mechanical keyboard. And a commit, okay, finally something that we recognize, right? So these three, blobs, trees, and commit, this is the very pulsing heart of Git. So let's start checking what is a blob. Remember when we said that Git stores content, not files? So every time you Git add a file, Git will store it, the content, only the content, as a blob. Blob is actually a technical term that means binary large object. And, well, originally it was not a technical term, just someone thought that the word blob is cool and they made it become a technical term. Believe me, that's true. And blobs don't have any kind of metadata, like file name, timestamps, extension type, nothing. A blob is pure content. And once a blob is created, Git compresses it and hashes it. And we will see this in practice in the command line. So let's add some content to our file because we just touched it. So if we cut anything, it will be empty. We added Santiago to Chile, which is suitable. And now we git add. So this means that the blob has been generated. And we will see again our folder. And before we had 3, now we have 4 objects in there. And let's cut the new blob. Cut file, so it should show, oh, I'm missing a -p, sorry, it just to pretty print. Santiago, you see, it's only the content, nothing else. Okay, but if a blob is just content, how does Git keep track of your file names and folder structures, for example? So for this, Git uses a tree. And we saw blobs are contents and trees. What are trees? Trees are simply pointers. And a tree will point to your blobs while holding the metadata information for the file name. And because this is Git, trees have their own hashes as well. So let's see for real what a tree looks like by pretty printing it in the command line. So let's go. There we go. This is all that there is to a tree. The first block here, this 106.4, is the file permissions. Okay, you might be familiar with this, with other stuff. Blob is just an indication of the object type. We have this long string that is our hash. This is the hash for the blob. And then we have the file name that is related to that hash. So this is a tree. Okay, but what if we have more than one file? What will happen? Will Git create another tree for another file? Is it, how's the relationship? So let's see that again. We will create 2 more files and do another git add to generate the blobs. And then we will confirm that the blobs are there. Okay, so we're adding. And then just checking that, just for educational reasons, just to check, okay, we have 6 files, so this means that the blobs were added. And let's print our tree again. So git cat file, I hope I don't forget the -p this time. No, I didn't. Good. And now you see you don't need to type the whole hash, just the 6 first letters will do. But wait. It's still the old one. Where are the new files? Well, what happens is that Git only generates trees once we run git commit. And trees can't be edited. So to get a tree with our changes, we need to create a new tree, and we have committed, and now we'll have a new tree. We will check again if we have any changes. Okay, we have 8 files. This means that something else has happened. And if we cut the new tree, there you go. You see the 3 blobs are there, each one with their respective file names. So that's how it works. You will not change a tree that is already there. You will just add one more. Right, but what about the folder structure? How will that work in Git? So let's create a new folder called Mercosur and move Argentina there because it's a member of Mercosur. And again, you already know the Git. Add, and if we run the status, we see that, okay, Argentina did move to Mercosur, which is great. And now we have to commit to generate a new tree. Right? And now we can cut the new tree that was created. Sorry, I forgot the -p. I always forget the -p. And if we cut the new tree that was created, we have a little thing that is different there. We have 2 blobs and 1 tree. And this is how Git keeps the folder structure together. So I think at this point it's better if we see a schema, right? So this is exactly what our repo looks like. We have 1 tree that has the picture of everything. Your repo can be seen through that tree. And that tree points to the 2 files that we had, and another tree that has, that is actually for the folder, you see? So that's how the Git keeps the folder structure, and it can get very complex, when you have, your regular project, your regular application. And as we saw, trees depend on our good old Git commit. But what is a commit indeed? Well, a commit is a pointer, and I must warn you, from this stage forward, anytime I ask what is whatever, you can say pointer, you will get it. Yeah, it will be right. So commits are just pointers. Their only job is to point to a particular tree and show the metadata associated to it. So let's see what a commit is made of. So let's print our most recent commit. And a commit is made of basically 5 elements. First, we have the tree, that is the whole snapshot of your whole repo. Everything is in that tree. Then we have a pointer to the parent commit. Of course, this will not be relevant for the very first commit because it won't have a parent. But yeah, you have a parent. That's how Git keeps track of your history. Then you have the author information and the committer information. In our case, these are the same, but there are some exceptions. In the old days, people would, edit patches and send them via email, and someone else would commit. So that would be the case where author and committer would be different. And then last but not least, we have the commit message that we very much appreciate. Right, so going back to the idea of the snapshot. Every time you commit it happens as if you were just clicking the shutter of your camera, and that's the job of Git commit. It will capture whatever was pushed to your index and generate a new tree. And besides that, Git also logs the metadata for the changes, as we just saw. And yeah, this is another way to see how the last commit holds information of the whole repo, and you can follow the arrows and see that everything is linked to that tree in the very top. That is our most recent tree. Right, and as we continue working, we keep chaining commit objects, and although time moves forward, a commit sequence will always point backwards to its parent. And in this example, every commit has only one parent, but multiple parents can happen if you have a merge from 2 or more branches. So now I think we covered the basics, because this is how Git works under the hood. And now that we've seen what Git objects are and how they interact with each other, there's a principle that you may have, by now worked out by yourself. It's the principle that Git objects are immutable, just like hieroglyphs carved in stone. And this could be, a Git Repo from the ancients. But what happens then when you find a typo? If things are immutable, what happens if you find a typo in your code or in your commit message? Well, you have to live with it, sorry. The best thing you can do is to correct your typo and then commit it again. So you will just generate a new corrected version, but the wrong version will be there forever. I'm so sorry. And some people may say, well, you can edit typos in your commit with git commit -- amend. But if that were true, it would mean that the objects are not immutable, right? So technically, this is not an accurate affirmation. And we will see what happens when you amend a commit. So we will create a new file again, now Colombia, and we will add a typo to the commit message on purpose. So let's type add Colombia with an extra A. And pay attention that when we commit, you see to F91 blah blah, that's the hash for the present commit. And now we edit the message and see again, we have a completely new hash. So you did not edit your last commit, you just created a new one and ignored the old one. So, there's a technical term for this. It's called self-deception. You are thinking that you edited, but you didn't. So, and all this object stuff that we talked about so far happens under the hood, and it's all good with machines. They are exceptional at doing the same thing again and again without error. But we're humans, right? And we need a way to keep track of our commits, because really, suppose that you worked all day long and you had all these commits, okay? You were on fire. And then you ask your colleague to review your code. And she's kind enough to agree, and she says, okay, send me the details. And you tell her, yeah, so just go to the commit H3LPME. It's not gonna work, right? We need a human-friendly way to handle, our work streams. And this is where references come about. That's the job of references. Unlike objects, Git references are subject to change. And the most famous reference in Git are the branches. Everyone has worked with one before. But what are branches? You know the answer? Pointers. Branches are only pointers. So picture it as a tour guide. When you go to London, there are those people with the umbrellas. They are doing the job of branches. Because a tour guide is not a landmark in itself. A tour guide will just walk around and show you, this is the landmark, now let's go to the next. So that's exactly what a branch does. So every time you commit, your branch will automatically move to the most recent commit on that stream. And the most famous or infamous branch in Git is called master. I know that GitHub has changed the default name to main, but Git hasn't. So if you create a new repo, you may have to change the name by yourself. And this is a paragraph from the book Pro Git, and it says, the master branch in Git is not a special branch. It is exactly like any other branch. The only reason nearly every repository has one is that the git init command creates it by default, and most people don't bother to change it. So, if there is nothing special about the master, let's call it main, if there's nothing special about main, Does it mean that even main is just a pointer? Well, I know you're not satisfied with just me saying, let's see it. So let's bring back our repo, and you see there the last one is refs. We have new files there because now we have real objects. But if we see whatever is inside refs, you will not see the name branches because the technical term for branches is heads. But if we see what heads we have inside, we only have main at this point. And if we cut it, what do you think we'll show? A hash. That's it. A branch is just pointing to this hash. And if we cut the hash to see really what this hash is, surprise, surprise, it's a tree. So that's the tree that is the most recent one that defines that branch. Okay, so if branches are pointers, what happens when you delete a branch? Raise your hand if you never worried about someone deleting your branch and you got really angry at them. You see, everyone. Guilty as charged. So, the good news is that next time someone deletes a branch, you can just say, okay, whatever. Why? Let's see. So, let's create a new branch called Africa. And now we will go back to our head folder and see what branches we have there. And we have Africa and main, and now let's delete one, and we're not deleting Africa. We are bold, we will delete main, okay? So let's go. Oh my God, I deleted main, what will happen now? Guys, don't fret. Remember, it's just a pointer. Your content is still there, untouched and beautiful. So let's, okay, I know you're not convinced. So let's check out this hash that we have there that was associated to main. And see, head is now at Colombia. That was our last commit. You know, there's all this text about detached head. Like, don't worry about that. We'll get that later. But, you know, you haven't lost anything. So what you can do is just to create a branch out of this hash. And you can do git switch -c, which is kind of the same as checkout -b, if you are more familiar with that. And okay, looks like we have a new branch called main. I don't believe it. I want to confirm it. There you go. Main is back. Well done. But please pay attention. This is a local repo. So do not try this at work. If you get fired, I will not accept, blame for it. But, well, you can rest assured because most people that work that are in a work context, they use GitHub, GitLab or something like this, and they have a protection for the main branch, so it will not be deleted. So, yeah, you cannot impress your colleagues with your confidence. Right, but a word of caution now. Please note that a Git commit chain that is not associated to a branch will eventually be deleted by Git's garbage collection. And there is a default grace period for the garbage collection, which is 90 days. So, well, and this grace period is customizable. And if you don't want to wait for the garbage collection that happens automatically, you can trigger one using git prune. But when this garbage collection happens, all the orphan commits will be deleted. So play around with your, branchless commits, but remember that eventually they will be deleted. Right, so when you create a new branch, Git will create a new reference. And let's suppose you create a new branch called feature using the git branch command, as you can see there. So the same commit now has two different references, main and feature. How does Git know which branch you are currently using? Because if you commit now, your branch needs to move on with you, but which one will move with you if you have two? That's where the uppercase head comes to the rescue. Well, in Portuguese, we have a saying that when something is very difficult, we call it a beast with 7 heads. And now you know that Git is a beast with way more than 7 heads. But we have an uppercase head that, from the user perspective, helps us tame all the others. The uppercase head is, again, what is it? A pointer. Well done, well done. It's just a pointer.
Is it going to be a trick question? Like, what is a pointer?
Well, you have to wait and see. So it's just a pointer, and like your head, it will go with you wherever you go. So it's just a way for Git to know actually where you are working. And the head will by default show the last commit on that branch. So when you check out or switch, they do the same thing in this sense. You are simply moving your head from main to feature, for example. So now if you commit, Git will know that the branch that needs to move forward is feature, not main. Other things happen when you do a checkout, but we're just looking at the head movement here, okay? And if you can check out a branch, remember a branch is just a pointer, you can check out any commit too. So if you want to go back to that very first one, you can. You can just do git checkout and use the little hash. And this is what Git was complaining about earlier. This is the detached head state. Because unless you have felt prey to the French Revolution, your head will be attached to you and it will go with you wherever you go. So even if you abandon your branch, your head will not abandon you. Lucky us. So this detached head is a weird terminology, but it just means that your head is not attached to your branch anymore. That's it. As long as you remember that, because again, garbage collection, if you keep working there and branch your whole feature out of this, you'd better put a branch on it. So yeah, ask your local council where garbage collection happens, okay? So now we have the proof that references change. Because the objects are immutable, but the references are not. So there you have, we checked out main, and if we cut the head, that file that we said wasn't too important for the beginning, you see it's pointing to another ref. It's not pointing to the commit associated to that ref, it's pointing to a ref. And every time you check out, your head will change as well. And that's it. Basically, that's how the head work, the uppercase head. And we have another type of reference, that is tags. It's the last type of reference, actually. And there are two types. This one that you are seeing there is the lightweight one. It is a reference because the only thing it does is what? It's a pointer, again. So there will be no metadata associated to it. So it's just like, the flag that is in the moon, that you put it in there and leave it there in the code, immovable forever, ever. So that's what the tag does. And in this way, it's different to a branch because the branch moves and the tag won't. But there is a different type of tag, which is the annotated tag, and this one behaves as an object. So as it is an object, it gets the full Git treatment, checksum and proper message and a date and an author for the tag. So if you are tagging a release, for example, the annotated tag would be the most appropriate one to use because you would have all this metadata to know when was this tag this release and who tagged it and all this stuff. Right, and to create an annotated tag, this is the command. The -a indicates that it's an annotated tag, and then you add the name and then the message. And a very important thing to note is that when you push stuff to GitHub, GitLab, Bitbucket, whatever, tags don't go with it. You have to intentionally push your tags using either those commands, or push origin and a specific tag, or push origin -- tags to ship them all to the cloud. Right, so, and although the annotated tags are objects and the lightweight ones are references, they all live in the same folder. So if we go to refs, you have that subfolder called tags, and then both type of tags will live there. Right, so let's now talk about history, because we covered already everything that is in our repo. You are now experts in Git Repo, right? And you may have realized that Git is awesome at predicting your past, because Git knows what you did last summer. And the first way to see what happened before is using Git log. Git log works pretty much like this photo there, this lovely family. You know that you have this baby and the mother, grandmother, great-grandmother, and that's how Git log works. It works like an ancestry list, that it goes upstream to the repo's ancestry, and you're looking at each repo's commit. And this is what Git log looks like, but you can use flags to customize it and make it a bit more user-friendly. So this is one option, for example. And I found out that there is this secret sport of customizing your Git log, and people go super crazy, you know, and add new stuff. And just note that I'm not here to make you copy commands. I just want you to understand Git. So I'm happy that I'm making you curious about that. So please tag me next week on Twitter, like, oh, this is what a great Git log looks like. I'd like to see that. And another way to see your history is using Git Reflog. And the difference here is that Git Reflog will not look at your parents, it will look at your own head. It's for grown-ups, right? So a reflog can be compared to animal tracks in the snow. You know, it shows where the animal has been, regardless of boundaries. If it changed to another person's property or another country, it doesn't matter, it's the track. So it's basically a way to do Ctrl-Z on your way on Git. It's like literally retracing your steps. And this is what reflog can look like. And if you see there, it shows when I checked out, it shows when I moved from Maine to Africa. That's pretty cool, I wish I could. And remember also that Git Reflog is only local, so when garbage collection happens and your orphan commits are gone, they will be gone from Reflog as well. But this is a very, very helpful command to find yourself, you know, if you freak out because someone deleted your branch, this is where you want to go to find what was the hash for the branch. Okay, so now that we are approaching the end of this, how does all this information of Git under the hood actually help me? You know, there's more to be said about Git internal workings, like we haven't talked about the 3 Git trees of Git, but what we covered today is enough to give you a very good start. And for example, now you can keep your cool in most situations, because you know that your content will be mostly safe from harm all the time, even if someone deletes the main branch, right? And there are certainly a few risky operations that may cause you to lose your content, but you will rarely lose content unintentionally, because Git is really good at protecting you against this data loss. Another thing that can help you is a better use of commit messages. You know, if you have a commit message history like this one, how will you know when a bug was introduced, or which commit changed your box to a triangle or whatever? So and the thing is, because we use all these tools like GitHub, GitLab and stuff, we become too reliant on PR, you know, or merge requests, because, you know, someone will tell me everything that changed, so I'll just wait for the PR. But then, if we have to debug something, we can't. We can't cherry pick stuff, because, you know, people do these huge commits with, you know, the whole feature in only one go. But if you just want to revert one little change that was done, you know, you have to work it out by yourself, and again, rework. So I hope that with this presentation you can see how short commits and straight to the point and effective messages can be really super helpful for your day-to-day. And another thing that you can do is change history. You know, Marty McFly is not there at random. This is a bit of a controversial topic, and people can have very strong opinions about changing Git's history. But there is one thing that unites all tribes. You should never change anything that has been pushed. If it's public knowledge, it's game over. Don't mess with it. Feel free to change history on your local repo, but don't mess with whatever is shared. And what do we mean by change history? I mean, for example, amending commit messages because of a typo, or reordering commits, you can do that. Or squashing several commits into only one if you see the need, or doing the reverse, splitting commits because someone committed a feature in only one go. And there's loads more that you can do just by playing around with your history. And yeah, I hope you find this interesting and try again. But now let's try to see how we can reason our way out of trouble using this information. So let's see one of the most common commands in Git, checkout. Let's go to the source. What is Git checkout? There you go. It's not a pointer. So checkout works to switch branches or restore working tree files. You see, that's the textbook definition. So we know we can use Git checkout to switch branches. But note, there is a restore there. So something else will happen as well. Right, I can switch branches, but can I switch to a branch that doesn't exist yet? Yes, you can. It's there in the instructions. The flag -b will let you create a new branch. And there is a very nice thing about this resource. It's, sometimes you are working on your master branch and you don't realize it, and then you freak out instantly, like, oh my God, I'm checking. What do I do now? Do I have to copy all these changes to, Notepad and then get a new branch and copy? No, you don't need to do that. If you do git checkout -b, all the changes that are in your working files will be transferred directly to the new branch. So that's a very useful thing that you can do, and I do that all the time because, well. And okay, checkout also mentions restore. So does it mean that I can restore a file that I just ruined since my last commit? I added all these functions and now everything's broke. I just want my file as it was. Yeah, you can just do git checkout and add the path. That's as simple as that. A lifesaver, many times. Okay, but restore is just a copy-paste from a certain commit, isn't it? Then can I restore a file from any commit in my Git log? Yes, you can. So just do git checkout and the full path to the file, and then you can have a file that your colleague was working on. Now it's yours. And if I can restore a commit, can I certainly restore one from a certain branch? Yes, if your branch is broken, feel free to just, check out all the files that are actually working from someone else's branch. And to close, I just want to leave you with this quote that is from a book called Death Comes at the End. Not a great title for this presentation. It's a book by Agatha Christie. And it says that fear is incomplete knowledge. And I hope that in this presentation we can we have built up a bit more of your knowledge in Git, and that this will help you conquer your fear and boldly go. Next time that you feel fed up with not knowing what the heck is going on, please go explore and come back to share with us, because taking action and sharing information is the only way we have to move forward. Thank you.